So, the way we're going to start class today is we're going to start talking about elevator questions, which are a very basic type of Newton's second law problem. Okay? When it's actually an elevator, people generally do them correctly. This is an elevator question, but it's not an elevator. Okay? Because it's a ball being thrown up in the air. So how many of you, when you drew this free body diagram, which we talked about the other day, did this and said, okay, this is 0.35 kilograms. And said, good, I got it all. Exactly. What about the force of gravity? Okay, that's what's most commonly missed in an elevator question where I say a ball or a rock or anything is thrown straight up in the air. People forget all about gravity for some reason and figure they can put these things into orbit. Okay, because that's what would happen here in this diagram. Right? What we have to remember is that there is also a force of gravity that is acting down. Now, we calculate the force of gravity by taking mass and multiplying by 9.81, or whatever we're told little g is in that situation. Okay? Most of the time it's going to be 9.81. So in this case then, I'm going to take 0.35 and multiply by 9.81. All right, so I've got a force of 3.43 downwards. Okay, what's my next step? I'm trying to calculate the acceleration of the ball. What do I need to calculate next? The net force. Okay, would I use m times a or sum of all forces? Sum of all forces, because that's what I've got. All right, so I'm going to go F net equals 12 minus 3.43. Okay, and I'm going to use all of my numbers when I do that. So I'll go 12 minus my answer. And 8.57. And that'll be up. Okay, what's my next step?
Find your acceleration, so I go acceleration is F net divided mass.
Right. Okay, so that'll be 8.57, okay, divided by the mass, which we were told was 0.35 kilograms. Right, so the acceleration of the ball is going to be 24 meters per second squared up. Okay, is that like a fairly basic question?
Yes.
Yeah, like it's no harder really than the ones we did yesterday with, you know, friction acting one way and people pushing the other way. We just have to remember that for an elevator, gravity is going to be one of our forces.
The way I did it was I did it like the 12 newtons and then divided it by the mass, and then took that number for the net force and then subtracted 9.81 and got the same answer.
Okay, so what you did is the differential acceleration method, which is one of the things I'm going to go over today. It's perfectly valid to do it that way.
Okay,
Yeah.
so I was just about to say I got like the exact same
And
answer,
you would.
just did it
Yeah, and I'll explain why you did in a little bit. Okay, can I get all those quizzes right up here in a nice neat pile, please?
Can we count the last questions? Because no matter what.
No, because I hadn't gone over it yet. It's hardly fair.
So then.
Okay, so with elevator questions, okay, we are always going to have gravity acting downwards, okay, as one of the forces, and then likely a tension or some sort of lifting force or pushing force going upwards. If it's actually an elevator, then it's going to be tension because elevators are lifted by cables. Okay? If it's something being thrown into the air, then it'll be the force of the hand throwing it. Okay? So we still want to draw our free body diagram. Okay, so they've conveniently also drawn us a box here for this particular one. Okay, and we know that the combined mass of the person and the elevator is 600 kilograms. Okay, so they also tell me that the elevator cable is exerting this tension force of 6,500 newtons upwards. I know that gravity is also acting downwards, but I don't know what its value is. Can I calculate it? Yes, I can, because I have mass, and I know what G is, because unless I'm told otherwise, I assume that this elevator is located on Earth, and that G is 9.81. Okay, it's usually a safe assumption. All right, so I'm going to take my 600, and I'm going to multiply by 9.81, and I'm going to get 5,886 newtons. All right, what's my next step if I'm trying to find the acceleration of the elevator?
Subtract your, the upward force by your, the force of gravity.
Right, I got to find F net, which is vector sum of all forces in this case. 6,500 minus 5,886 is going to give me 614 newtons up. So this elevator is accelerating upwards. I'm supposed to find out how fast. So the acceleration will be F net divided by m. 614 divided by 600 is going to give me like 1.02, I think.
1.02.
Yeah. Okay, so just 1.02, because I have three significant digits, okay, times 10, no, just 1.02 meters per second squared. Up. Okay? Now, if I'm in this elevator right now, how do I feel? And I'm not claustrophobic or anything like that. I mean, do I feel heavier or lighter? I feel heavier. Yeah. If the elevator is accelerating upwards, the floor pushes on my feet harder than it does if the elevator is stationary. That's the only way I get accelerated upwards along with the elevator. Okay? Similarly, I'm sure you've all ridden in an elevator at some point. When the elevator descends, there's that moment where it first starts to descend where you feel a little bit lighter. Okay? Maybe if it's an older elevator that's poorly maintained, it feels like it's going to fall. Okay? That's the brake releasing and letting the elevator accelerate downwards for the first couple of seconds. Elevators, unless they're going to the top of a really tall building like an express elevator, typically don't accelerate to great speed or for long periods of time. Okay? If you're just going to the top of, a 5-floor building, it's not going to move very fast. It's going to accelerate for the first couple of seconds at a slow rate and then travel at a constant velocity after that. Okay? If it's an express elevator, like maybe you're going to the observation deck of the Empire State Building, that elevator is going to accelerate at a low rate for a longer period of time because it doesn't make stops at the lower floors. Okay? But it obviously doesn't want to accelerate at a high rate because that would be uncomfortable to the occupants. Okay? Now, what often happens with elevator questions is they'll give you this ridiculous situation. A person stands on a scale in an elevator because people do that. Okay? And the elevator accelerates upwards. The scale reads this many newtons. Which force is that? Gravity or the upwards force?
Would it be gravity?
It's the upwards force. Remember, the scale isn't reading your weight unless the elevator is stopped. Okay? Then it's reading both the upward and downward forces because they're equal because you're not accelerating. But if the elevator is accelerating upwards, what the scale reads is how hard the floor is pushing into your feet. That's the upward force. Now, if it's accelerating upwards, that force is greater than your weight. Okay? If it's accelerating downwards, that force will be lighter. And so you'll go, yay, I lost weight, because the scale will read that you're a little bit lighter, until the elevator stops accelerating. Once the elevator reaches a constant velocity, what's the scale going to read again?
Your body weight?
Yeah, your normal weight, because once you're traveling at a constant velocity, the net force is 0, and the upward force and downward force balance again. Okay, does everyone kind of follow me on that? So that's a typical situation that you might get on a worksheet or a quiz or something like that, where it's a person stands on a scale in an elevator. Kind of silly, but it is something that they talk about often in physics textbooks for whatever reason. Okay. T, question?
I just had like a comment thing. Do you like, when the elevator comes to a stop at like the top, do you also like jump to see if it'll fall back down?
Well, I mean, theoretically, if you could time it, right, you could be able to use some of your like momentum as the elevator slows. If you jump, you technically jump higher from the floor of the elevator than you normally would, because you'd be using your momentum.
Yeah, but
And the elevator would stop.
Because I mean, like when it comes to a stop, like as it comes to a stop, you're leaving it.
Yeah,
And
your
so
inertia carries you.
And because it's still upwards, by the time it starts falling back down a little bit to rest itself on the same platform, you land on it. Do you also do that and then see if it'll like?
I don't know, because I don't want to fall.
No.
Yeah. It's not the fall that frightens me, it's the sudden stop at the bottom.
This might be like a long question, but like, how did they discover the force of gravity? Like, how did they discover that it was 9.1?
Well, that's what Newton would tell you. But that's actually Newton, that's how he came up with his universal law of gravitation. And it discovered, in that discovery, he noted that the Earth and the apple are attracted to each other. But we only see the apple falling because that's our reference. The Earth doesn't really move in regards to that. So there was a lot of experimentation that went on that was related to how objects are attracted to each other due to their mass. So we get into that more in Unit 3.
Isn't that why like the Earth rotates the sun? Because it like pulls in because of the mass?
They attract each other. That's how they detect exoplanets around other stars. It's one of the methods they use. They observe the star, and the star will fluctuate. Not because, we got the one method where it gets eclipsed, but the other one is the movement of the star because of the other planets around it. Okay, so like our star wobbles back and forth because Jupiter, which is very, very big, pulls it towards itself. So as Jupiter moves in its orbit, an observer somewhere else would see our star move away and closer, okay? And so from that, they can figure out the approximate size and the distance of the exoplanets, and that's what they do. It's a lot of math.
I will watch.
Okay, I'd like you guys to try these two. Number 2, you'll probably have a little bit of trouble with, because that one is going to be the differential acceleration method that I haven't gone over yet, but sometimes people just intuitively figure it out. So give question number 1 a try. It's the same elevator, so it's still 600 kilograms. Okay, see if you can find the acceleration of the person when the cable force is different, and then try number 2. All right, so I'll give you guys a little bit of time on that. Okay, so in this example, in question number 1, all they've done is change the tension that's pulling up on our 600 kilogram elevator. So now the force upwards is only 5,200 newtons instead of the 6,500 it was in the first example. This number here is still the force of gravity, and because we haven't changed planets or changed elevators, that number hasn't changed. It's still 5,886 newtons. Now which way is the elevator going? Down. Down. It's accelerating downward because now our net force, okay, is 5,886 minus 5,200, which is 686 newtons down. Okay, so our acceleration then is going to be 686 divided by 600, which should come out to 1.14 meters per second squared down. Okay? So an elevator doesn't lower you by just releasing the brakes, right? The electric motor just doesn't pull hard enough to overcome gravity, which slowly lowers you down to the ground. Okay? All right. for question number 2, okay, I want you to give question number 2 a try, even though it's going to seem like it hasn't given you enough information. All right, so give number 2 a try. All right, so this one here, we have to solve a little bit differently, and we do that by recognizing how we can calculate individual forces. Okay? Newton's second law says that F net is mass times acceleration, but we never write this part, which should really be there. It's the net force is the mass times the net acceleration produced by all the forces that are acting. Okay? We do write this one this way. Okay? To calculate the force of gravity, we multiply the mass by the acceleration that gravity produces. Well, any individual force can be calculated that way. Okay? It would be force 1 equals mass times acceleration that that force could produce if it were alone. Okay? So that formula is basically true for any individual force. Right? So when I'm looking at the chain hoist question, okay, I don't know what the mass of the engine is. It's what the question is asking me to calculate. Right? What I do know is that there's an upward force, which I'll call the hoist force because it's coming from the hoist, okay? And that is 2.85 times 10 to the 3, so 2,850 newtons. Right? I also know that this is an elevator. And so there should be a force of gravity down here, which I would calculate by going m times g. Problem is, I can't do that. Because what am I missing? I'm missing m. All right. So this is usually where people get stuck. Because they're like, I don't know what to do now. I don't have mass. How am I supposed to calculate this force I need? Where do I go from here? Well, this is where we go from here. We do the vector sum of all forces. And we say that the force from the hoist, even though we know the number, okay, is the mass times the acceleration from the hoist. Okay? Plus mass times the acceleration due to gravity, which gives me the mass times the acceleration net. Okay? Is that the vector sum of all forces? All right. Now, I know what this force is. I know it's 2,850 newtons. Right? I know that the hoist is going to produce a net acceleration of 1.5 meters per second squared. So I know what A net is. So what I'm going to do now is kind of write my givens here, and I'm going to say that I know the force of the hoist. I know the acceleration that all of these things together produce. Okay, so what can I cancel from this equation? What's in every term? Mass. Now, this also tends to kind of confuse people because mass is what I'm supposed to calculate and I'm canceling it, but there's a reason for my madness. Okay? I'm going to cancel off the masses. Do I also know this number?
Yeah.
Right. Okay. So if I know G and I know A net, can I calculate the acceleration this force would produce if it was by itself? Can that help me get the mass? It can, because 2,850 newtons equals mass times the acceleration of the hoist. So if I can find the acceleration of the hoist, I already know the force of the hoist. I can use that to get the mass. That's the differential acceleration method. I'm using the difference in the accelerations to get something else because I don't have the mass. And that's when you have to use this method, when you don't have the mass and you actually can't calculate the forces. So what I'm going to do is say the acceleration of the hoist equals the net acceleration minus g. Okay, and so I'm going to go 1.5 up minus, okay, 9.81 down. So I'm actually subtracting a negative here. Okay, so I get 11.31. So if there was only the hoist, okay, if there was no gravity, the hoist could accelerate the engine at 11.31 meters per second squared. Okay, so what we have to understand here is that the vector sum of all forces works exactly the same as the vector sum of all accelerations, because they have in common the same object, the same mass. Okay, so there's some that should work. Okay, so now that I know this, now I can go back up to this formula. I know the acceleration of the hoist because I just calculated it using differential acceleration, and I know the force of the hoist. So now I can solve for mass. I'm going to take the force of the hoist and divide by the acceleration the hoist would produce. $252 kilograms. So that's over 500 pounds, actually closer to 600 pounds. Yeah? I don't know if anyone's ever seen the Fast and the Furious, but there's a scene where Dom holds, he kicks out something that's holding up an engine, and then he grabs the chain that's connected to it, and he holds the engine with one giant Vin Diesel arm over top of the guy. No. I don't care who you are, or how strong you are, nobody's holding with one hand, one arm, 600 pounds, okay, without, dropping it. That dude should have been dead, okay, because, there's no way somebody holds a 600-pound engine with one hand.
We should watch the video clips.
I don't have it. Okay, that makes sense? Our differential acceleration? Okay. Then, try this one, because it uses differential acceleration, okay? If you're skydiving and you jump out of the plane, okay, you've got the force of gravity acting on you, so they've already kind of done the free body diagram here, okay? And the force of air resistance acting up. All right, so what we're looking for is the mass of the skydiver, so same method. Okay, so we're not told the mass, we're being asked to calculate it. So what we're looking for here is still a vector sum of all forces situation. F net is still gravity plus the force of friction. But what I want to do is expand this out so that it looks like this. Mass times A net equals mass times gravity plus mass times the force of friction. Or sorry, the acceleration, not force. The acceleration due to friction. All right, so now I can eliminate mass. Okay, they do tell me the net acceleration. They tell me the I know the acceleration due to gravity, so all I have to do is find the acceleration, okay, due to the force of friction. So I'm going to go A net minus the acceleration due to gravity equals the acceleration due to friction, okay, and so that's going to be negative 5.60 minus negative 9.81, and that'll give me the acceleration that the force of friction would produce by itself. Okay, so negative 5.96 minus negative 9.81 gives me 3.85 meters per second squared up. Okay, now I'm going to go back to this. The force of friction equals mass times the acceleration due to friction. They told me the force of friction is 250. I just calculated the acceleration due to friction, so now I can calculate the mass. Okay, so that's going to be 250 divided by 3.85. Okay, so they have a mass of 65 kilograms. Okay, it's not often we run into a differential acceleration method question, but it's still important to understand the relationship between mass and acceleration for individual forces. Okay, that m times a applies for any individual force. Okay, all right. Okay, I want you to try these two with the bungee jumping. Just gonna make this small enough to fit on the screen. Okay, is a bungee jumper still an elevator? Yes, the reason you fall is gravity. Okay, the force upwards is the bungee cord, which you will pray is there. Okay, without the force of the bungee cord, bungee jumping is much different. Okay, and tragic. So we want to make sure that we have that force upwards acting on the person. Okay, now they tell us that person is 55 kilograms, so we've got the mass. We don't have to use the differential acceleration method for this question. Okay, they tell us the bungee cord is exerting a force of 825 newtons upwards. Force of gravity is acting downwards and has got to be smaller than that because she's only 55 kilograms. Okay, so if we go 55 times 9.81, we'll have her force of gravity, 539.55. Okay, so that equals Fg. So now, can I calculate the net force?
Yes.
Okay. So mathematically, this is a pretty straightforward question. F net is going to be the vector sum of all forces, 825 minus 539.55. All right, so there's my net force, 285.45 newtons. Okay, and now I can calculate her acceleration. A equals F net divided by m, so 285.45 divided by 55 kilograms. All right, we only have two significant digits. Yeah, so 5.2 meters per second squared. Which direction? Yeah. Okay, everyone all right with that? Okay, so question number 2 is not at all about the math. Question number 2 is about understanding what's going on in terms of forces and vectors. Okay, so if she jumps at the lowest point, okay, her velocity is 0, which is the exact opposite of the highest point when you throw something up in the air. Okay, but it's a similar situation. So she's falling, 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 but the bungee cord is pulling, 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 okay, until eventually her acceleration has produced a velocity of 0. Right? Now, her direction of her acceleration at the lowest point to when she was accelerating due to gravity. Her acceleration at that lowest point is which way? Up. In fact, it's at its maximum amount. Okay? The more you stretch a rubber band, the harder it pulls. Okay? This question is simplified a little bit, okay? Because the upward force of the rubber band would actually change as you stretch it. Okay? But definitely at the bottom, that acceleration would be at its maximum and it would be upwards. Okay? At this point, what is the direction? Definitely up. Okay? All right. Now, do I want to get into system questions today? I think I'm going to have you work on some simple Newton questions before, and we'll get into systems maybe tomorrow. So, in your digital workbook, the first page starts out with Don't look at my password. It's all dots. It's just like yours. Okay. Maybe not. That's better. Okay, so in your digital workbook, and it's going to be on one of the first pages here. Okay, I would like you guys working on Newton's second law worksheet number 1. These first few are really easy. They're like the stuff we were doing yesterday, just F equals m times a. Then it starts bringing in a little bit of vector stuff as we go along there. Okay, but let's work on like the first dozen or so here today, okay, and then we'll start getting into, there's an elevator question on number 13 is an elevator, okay, so you can probably try that one as well. In fact, let's say start with 13. Okay? Do the elevator question first, and then work backwards to number 1. Okay? That way we can go over number 13. All right, so as always, we want to start with our free body diagram, because that's kind of our givens here. So we have a 1,200 kilogram elevator. Okay, the forces acting on the elevator are gravity, and that's going to be 11,772 newtons, yes?
Yeah.
Okay, so that equals Fg. All right, and then we're going to have the tension in the cable, which is going to be variable here. Okay, in situation A, it's going to be one value. In situation B, another value. It's not always the same. Gravity's always the same because it's always Earth in this elevator. Right? So we've got that force acting up. So it says, calculate what the tension in the cable is when it's accelerating downward at a rate of 1.05 meters per second squared. Okay, what can I calculate right now since they told me the acceleration and the mass?
Your force.
I can calculate my net force. So for part A, my F net is going to be mass times acceleration, 1,200 times 1.05. Okay, so my net force is 1,260 newtons. Up. Okay, what's the other way to calculate F net?
Your sum of forces.
The sum of all forces. Okay, do I know two of these?
Yes.
Yeah. So I can calculate the tension now because I calculated the net force already, and I know what the force of gravity is. Okay, I don't know if you remember, but the other day when we were first talking about this, I said you're going to use both methods in almost every problem you do. You're going to have to do mass times acceleration and the vector sum of all forces. Sometimes you'll do MA first, and sometimes you'll do MA last. It all depends on what the question's asking for. Usually, if it's looking for a force, you'll do MA first. And then you'll work backwards from the sum of all forces to an individual force. If it's asking for acceleration, you'll know all the individual forces. You'll go to the sum of all forces and then do MA. Okay? So in this case, I'm going to isolate the tension by simply going F net minus Fg. And I have to keep vectors in mind here now. This is 1,260 newtons minus negative 11,772 newtons. Okay, and that's the mistake people make most often, is they forget to make gravity down. Okay, so if I do that, I'm going to get 1.05 times 10 to the 4 newtons. Okay, oh sorry, that's supposed to be downward. I did this all for upward. So we just did B. Sorry guys, I didn't read the question very carefully. We just did B where it was accelerating upwards, okay, which is why we should get this number. Okay, what changes if it's accelerating downwards at 1.05? Nope, gravity doesn't change. That number becomes negative. Right? That's all that changes. It's the same acceleration, all that changes is the direction. So instead of being positive 1,260, now it's negative 1,260. Okay?
Oh, because it's going like you're lowering down.
My net force is downward, so my acceleration is downwards. Okay, that's all the changes for part A and part B. Now, for part C, here's the trick.
The constant velocity.
Anytime I see those words, F net is 0. Okay, I have to be on the lookout for those words because they come up a lot during these kinds of problems. So if it's traveling at a constant velocity, that means that 0 equals tension plus the force of gravity. In other words, they're equal in magnitude, but opposite in direction. Okay, the force upward and the force downwards balance. That's why they add up to 0. Okay, so I have to watch for that. Anytime it says a constant velocity, it's actually given me a really big piece of information. It's told me A is 0, F net is 0. Okay, and that can be really helpful when I'm doing calculations to know that. Okay, questions on 13? That is a very typical elevator question. Okay, try that one. We did one like that kind of at the beginning. That was kind of like Teddy the Wonder Dog. Okay, so on this one here, we don't even really need a free body diagram because there's only one force. It says it's a horizontal frictionless surface. Okay, so if it's horizontal, normal force and gravity cancel each other out. I don't even need to put them on there. The only force that's acting, okay, is the net force. Okay, whatever it is, whatever that pushing or pulling force is, it's the net force because it's the only one. Okay, so what I've really done right there is the vector sum of all forces. There's only one force. Okay, so I need to calculate the acceleration. And I know that it accelerates from rest to 4, moving 5 meters. So I would say I'm probably going to be using this formula. Okay, because I know A, I know D, or sorry, I'm looking for A, and I know the two V's and D. So I'm going to have VF squared minus VI squared over 2D. So for this question, that will be 4 squared minus 0 squared divided by 2 times 5. Okay, so 16 divided by 10, okay, should give me 1.6 meters per second squared, and that would be positive or forwards. And then I just have to divide that by the 12 newtons. Okay, so 12 divided by 1.6 should give me 7.5 kilograms. Okay, tomorrow we're going to move into some more challenging Newton's second law questions. We'll probably talk about systems and pulleys because Tuesday of next week we're going to do our lab on Newton's second law, and we've got to understand how pulleys and systems work because it'll involve pulleys and systems. Okay, so that's where we're headed going forward here.